Problem number 3. These are getting really good. This one involves hydroxide concentration. And so we're looking for the hydroxide concentration in a salt solution. I recognize sodium cyanide as a salt, and then I'm given a Ka for an acid. All right, so where do we start with this? Well, first of all, let's take this salt and let's write the reaction in water. So this is a solid, and when we dissolve that, this thing completely ionizes. Okay, this is sodium cyanide. So these are aqueous solutions. But then this cyanide ion, what does it do in water? Well, it will actually grab water molecules, and what will it do? Form equilibrium with hydrocyanic acid. That is a weak acid, and we will kick off some hydroxides. Okay, so what we need to recognize is this is a conjugate base. All right, have you heard that term? Conjugate base. Okay, so what's going to happen? Well, in water, this salt solution is going to produce some hydroxide ions. So we need to figure out that concentration. All right, so what we're going to do is let's start with the given here. We're given a concentration of 0.1 molar. So I know that every one of those sodium cyanides will break apart. And so I know that the cyanide concentration is 0.1 molar. Okay, and then some of it is going to dissociate. And I'm going to call X. Looks like I'm doing a little ice diagram, doesn't it? I am. Kind of like a mini ice diagram. So my concentrations at equilibrium for both of those are going to be what I call X. They're going to be the same. Well, where does that come from? Well, we'll have to react away X amount of that cyanide. Okay? So if we were to write an equilibrium constant for this guy, it would look like this. The Kb, because this is a base, it's going to be the concentration. Let me just go ahead and write this before I talk. Of HCN times the hydroxide, and on the bottom we would have that cyanide ion. Okay, well, if we go ahead and plug in our x's, we get x times x, or x squared on the top, and on the bottom 0.10 minus x. Okay, now if only I had a Kb. What do I have here? I'm given a Ka for the conjugate acid. So how do I get a Kb? If you go looking for that, you probably won't find it in a table. So let me show you how to get here. Well, you probably know that the acid and base constant, the product of them will give you the Kw for water. Okay, so if I'm looking for the Kb, all I need to do is take Kw divided by Ka. Now, Kw for water at the temperature where most of these reactions are occurring is 10 to the minus 14th. Remember, that sounds very familiar, right? You know the pH scale and all that. So the Ka that we were given was 10 to the minus 10th. So if we crunch the numbers for the Kb, we get 2.0 times 10 to the minus 5th. Okay? So this is a little trick. If you don't have a Ka or Kb, you have the other one. You can find it by using the Kw. All right, so I'm going to take that Kb over back to our problem, and let's finish this thing up. Okay, so my Kb that I just calculated was 2.0 10 to the minus 5th. And I'm sitting here with an x and a 0.1 minus x. And this looks horrible. It looks like we need to use the quadratic formula to solve for x. Is there a way around that? Well, there is. And here is the reason. This little guy right here is going to be very small. Okay, in fact, we're going to call that negligible, meaning very, very small. So that 0.1 minus x is approximately equal to 0.1. Okay, so how do I know that x is going to be so small? Well, the Kb is pretty small, and so I know that x is going to be what I would consider insignificant. So if we can drop that minus x, that makes the math a lot simpler. And so we would solve for x squared over 0.1. Can you always do that? No, you can't. But in this case, I think it's going to be a-okay. And so when we solve for x, we're going to get, let's see, 1.4 times 10 to the minus 3rd molar. Now, don't leave it like this, because what was x? Well, x was, what did we choose for x? this guy right here. X is our hydroxide concentration, so that makes sense. Let's go ahead and write that. And so, yeah, where did all that hydroxide come from? Yeah, that salt solution is going to create it. And I just want to show you this. This is not really part of the problem, but if you take the negative log of this, of course, you get the pOH. And the pOH of this guy would be 2.85. And then the pH, which is more interesting, the pH is going to be 11.15. And you say, wow, that's pretty high, isn't it? Yeah, it is. Where did it all come from? That is as a result of the salt, okay, creating all those hydroxides in solution. All right, this was a good problem, involved weak acid, weak base, Ka, equilibrium, dissociation, all those things. So I hope this one helps. This is a good problem. Go back through it step by step. You can do this.